we're going to dive into a hidden mathematical pattern that connects, well, pretty much everything, from the spirals on a pineapple to how computer networks find the fastest route. It's a code that shapes our world in ways you probably never even imagined.
Kind of weird group, right? It sounds like the setup to a bad joke, but the answer is actually this beautiful, elegant pattern. It's a sequence of numbers that nature just seems to be obsessed with. Let's see if you can spot the rule as we go.
Okay, so it starts with 1.
And then another one.
Then we get 2, 3, and then 5. You seeing the pattern yet? It's actually pretty simple. Each new number is just the sum of the 2 that came right before it. And that simple rule, it generates one of the most powerful patterns in the entire universe.
So yeah, this isn't just some random game of numbers. It's like a hidden code that pops up over and over again in the natural world.
This sequence actually has a name, the Fibonacci sequence. And once you know about it, you start seeing it absolutely everywhere. It's in the way a pine cone's scales are arranged, and the spirals of seeds in a sunflower. And it turns out this is like nature's most efficient way to pack things in super tightly. So where did this whole idea even come from?
Well, it was introduced to the Western world way back in 1202 by a mathematician named Fibonacci. And he used this really clever thought experiment to explain it. And it was all about rabbits. Okay, so picture this. You've got one pair of brand new rabbits. After a month, they can mate. A month after that, they produce a new pair. If this cycle just keeps going, how many pairs will you have after a year? The number of pairs you get each month, it follows the Fibonacci sequence perfectly.
All right, so to really get a handle on patterns like Fibonacci's rabbits, or, anything that changes over time in these little steps, we need a more general language, a mathematical language.
And that language, well, it's the language of sequences. A sequence is really just a fancy word for an ordered list. In math, we're often talking about infinite sequences of numbers. You've got a first term, a second term, a third term, and it just keeps on going forever.
So there are basically 2 main ways to define a sequence. A recursive formula is kind of like a chain reaction. It tells you how to get the next number from the ones you already have. The Fibonacci sequence is the perfect example of this. But an explicit formula, that's more like a direct flight. It lets you jump to any number in the sequence and calculate it directly without needing to know any of the ones before it. And this is where we get to the really big question about any of these infinite patterns. If it goes on forever and ever, where does it actually end up? What's its endgame?
To dig into this, let's check out a classic puzzle. Let me introduce you to Harry the Hare. He's walking to the grocery store. First, he walks half the distance. Then he walks half of the remaining distance. Then half of that remaining distance. And on, forever.
So think about it. First step, he's halfway there. Easy enough. Then he covers half of what's left, which puts him at 3/4 of the way to the store. Then 7/8. He's getting closer and closer, for sure. But with every single step, the distance he covers gets smaller and smaller.
So here's the million-dollar question. Will he ever actually get there? I mean, if he's always covering just half of the distance that's left, does he ever actually cross the finish line? It's a classic paradox that really forces us to think about what it means to reach a destination through an infinite number of steps.
Okay, to solve Harry's little problem, we need to bring in 2 of the most important ideas for understanding sequences: convergence and divergence.
A sequence converges if its numbers get closer and closer and closer to one specific number. We call that its limit. And for Harry, his journey totally converges to 1. So yeah, mathematically speaking, he makes it to the store. Now, the opposite of that is divergence, and that's when a sequence just doesn't settle down on any single value.
Now, divergence, that can happen in a few different ways. As you can see, a sequence can just shoot off to infinity, never stopping, or it can just plummet down towards negative infinity. And then there's the third kind, where a sequence just oscillates, bouncing back and forth forever without ever landing on one final spot.
Okay, hold on. There's one more really crucial distinction we have to make here. It's a bit of a subtle point, but it's absolutely essential for understanding how all these patterns work.
All right, so a sequence, that's just the list of numbers itself. For Harry, it's 1/2, then 3/4, then 7/8, and on and on. A series, on the other hand, is what you get when you add up all those numbers. It's the sum, the total. They're related, for sure, but they are not the same thing. Super important difference. One's the list, the other's the total.
So wow, we started with rabbits and pineapples, and now we're talking about infinite limits. Let's pull this all back to why any of this actually matters in the real world.
Get this, the Fibonacci sequence is not just some cute pattern in nature. It's a total powerhouse in computer science. It's the engine behind something called the Fibonacci search technique, a ridiculously efficient way to find data in a sorted list. It's also used in data structures that help algorithms find the shortest path through a network. Think about your GPS finding you the fastest way home. Yeah, that's this stuff at work.
And all of this really just leaves us with one big question. The Fibonacci sequence is just one of these mathematical patterns that's quietly organizing the world all around us, from nature to technology. So it really makes you wonder, doesn't it? What other invisible patterns are out there just shaping our world, waiting to be discovered?